Good morning, everyone. Today we are going to continue our talk about characteristics, applications, and processing of polymers. This is the part two of this topic. In last class, we talked about the first one, and we have um, learned several important concepts and important knowledge. And, uh, and there are several important things I want to refresh your memory. The thermoplastics versus the thermosets. And I told you last time that these two groups of polymers, they are very, very important in our daily life. And I want you guys to know and what these materials are and what mechanical properties these materials have and what are the examples for these two types of materials. We talk about thermoplastics and thermosets, and I also told you one useful technique to memorize to differentiate these two um, types of materials. The technique is that thermosets they are harder, they are hard and brittle, and thermoplastic they are soft and ductile. Remember this one. And I also introduced this figure and shows how the molecular weight along with the operating temperature and to determine the status of this material. And also melting temperature along with Tg, and Tg is the glass transition temperature. And to also talk about the influence of temperature and strain rate on thermoplastics. And so if you see this figure and you can conclude that um, if we increase the temperature and it becomes softer and also the ductile, increasing strain rate and have the same effects of decreasing temperature. And then we talk about these melting and glass transition temperatures. And then we talk about crazing. Crazing is a very, very important failure mechanism for polymers, especially for the thermoplastic polymers. So actually, it is at the very beginning they have fibrillar bridges and these microvoids. The microvoids come together, and then finally they form a bigger crack. These aligned chains here, you can see aligned chains. And then we talk about the new things. Um, we will talk about vulcanization. Okay, this is a vulcanization. And what is a vulcanization? Vulcanization means the cross-linking process in the elastomer is called vulcanization. I want you guys to know this, and which is achieved by a non-reversible chemical reaction, ordinarily carried out at elevated temperature. And in most vulcanizing reaction, sulfur, right? This is sulfur. The compounds are added and to the heated elastomer. Chains of sulfur um, atom bond with adjacent polymer. The backbone, the chains, and cross-link them, and which is accomplished according to the following the reaction. You can see, so this is a CCCC, right? So this is a CCCC here, and then M plus NS, we have this sulfur, and so S M S N, and in which the two cross-links shown consist of M and N sulfur atoms, and cross-link main chain sites are carbon atoms that were doubly bonded. These are doubly bonded before vulcanization, but after vulcanization have become single bonded. We can see clearly. So these are doubly bonded. But after this is we add this is the sulfur atoms and they become uh, single bonded. This is singly bonded and doubly bonded and singly bonded. So this is vulcanization and cross-linking. And so here this figure shows the stress strain curves to 600 percent elongation, very huge, this number. For unvulcanized and vulcanized, this is natural rubber. So this is unvulcanized. This strain, you can go very, very high, okay? This is a strain very, very high, and this strain, this stress is very, very low, is relatively low. For vulcanized, this is a polymer, natural rubber, and we can have higher stress for a given the strain when compared with unvulcanized the natural rubber. So this picture shows the effect, the influence of vulcanization for the mechanical property of this is the polymer natural rubber. So polymer formation. So there are two types of polymerization. One is called addition or chain polymerization. Another one is a condensation called step polymerization. So we have these are two different types of polymerization. I would suggest that you memorize these two the concepts. Then if I give you a problem to solve in either the following quiz or following exam, and you should be able to answer this question correctly. Remember doubly bound and this is singly bound. I just told you in previous slide. And then we talk about what these two polymerizations are. First one is chain addition, initiation here. So this radical are here, and then this radical attached with this is a mer, we call mer, right? Polymer. Mer is a repeat unit. Poly means multiple. And you can see here, this is a doubly bonded becomes singly bonded, and the bond, another bond is attached to this is the radical. And propagation. So you can see R here. Okay, see, and so here is has this one has one. So this one has this dot here, and so this is R. Then this is C. This is double bond, and will be open and become a single bond, and so this carbon and this carbon will be bonded together as shown in this one. So I mean, so here is the we call this is we call this one is a mechanism. Okay, this one has a tendency to capture another the carbon atom. So termination, you can see here. So here one will be determined. So this one and this one, these two guys, right? And these two guys, they will come as this is have a hydrogen. This one are have a C here, right? Have a H, give a H for this one. So then this is a C, this is a double bond, C. So here is R. Or we have these two guys, they come together, and we have this kind of combination. So this is called disproportionation. This is the word is very, very tongue twisting, and disproportionation. Okay, so this is disproportionation. So condensation is another polymerization. As the name suggests, condensation. Whenever we say condensation, what comes into your mind? For me, when we see condensation, I will say in some physical process or chemical process, I see the water, right? Condensation usually have the water, we form the water. So here is this is a polymer. So you can see this H and this HO, and these two guys come together, and then we will have a H2O, this water molecule. And but this one and this one, they form another the polymer. It's called a step polymerization. Does that make sense? Okay. Then polymer additives to improve mechanical properties, processability, durability, etc. And we have some polymer additives. For example, fillers added to improve tensile strength and abrasion resistance, toughness, and decrease cost. Fillers. Okay. For example, this carbon black, silicon gel, wood flour. This is the glass, limestone, talc, etc. And plasticizer. What is plasticizer? Added to reduce the glass transition. Plasticizer, temperature TG below room temperature. So this is very, very awesome. Presence of plasticizer transforms brittle polymer to a ductile one. Plasticizer makes something that makes that's enable plasticity. So this is the presence of plasticizer transform brittle polymer to a ductile one, commonly added to PVC, otherwise it is a brittle. Plasticizer, okay? Plasticizer means something, some matter that can enable another things to become plastic. Stabilizer. And stabilizer means that you make this is the polymer molecules stable. And for example, antioxidants, and to have and some antioxidants in the polymer so the polymer can withstand this is oxidation. And UV protectants and UV ultraviolet protectants. And lubricants added to allow easier processing polymer slides through the dyes easily. For example, sodium and stearate. And colorant, the dyes and pigments. And flame retardants, substances containing chlorine, fluorine, and boron, and flame retardants. So this is very, very important. Okay, so I don't know whether you guys know or not. In 2008, when Beijing held the Olympic Games, and the stadiums in Beijing, and the people, the authority asked the people to build these chairs, build these the structures inside the stadiums, and using the flame retardant material. So this is for this that kind of polymer, and we need to add these flame retardants. As I said, substance containing chlorine, fluorine, or this boron, and so these three materials can retard the flame. If there's a fire, the hazard and all the materials, they are not easy to catch fire. So this is very, very important for the safety and security. And processing of plastics. Thermoplastic, we know thermoplastic and thermostats. Thermoplastic is softer. Thermoplastic can be reversibly cooled and reheated, okay? Recycle, and heat until soft, shape as desired, then cool. For example, polyethylene, polypropylene, and polystyrene. And thermostat, we also talk about this one in our previous class. Thermostat means when heated forms a molecule network chemical reaction. So degrades, does not melt when heated, it degrades. A pre-polymer molded into desired shape, then chemical reaction occurs. For example, urethane epoxy. So this is a thermostat. Questions regarding this slide? And then we talk about processing plastics, compression molding, on thermoplastic and thermostats, on polymer and additives placed in mold cavity. Polymer and additive, we learned some additives here. And mold heated and pressure applied. A fluid polymer assumes shape of mold. as this is figure illustrates. So this is a die, heat and heat. This is a mold base. So this is a platen. So this is a mold plunger. So this is a guide pin, a molding compound. This is molding compound. Mold cavity. This is a platen. So this is mold base, hydraulic plunger, and sometimes we need to use very huge force. So that's the reason we use hydraulic. And plastic processing plastics, another one is injection molding. I don't know whether you have noticed this or not. We have injection molding downstairs and MDH building downstairs, and you can see that. All right, so on thermoplastics and some thermostats, when RAM retracts, this is RAM. On plastic pellets, these are small, the beads, and dropped from hopper into barrel, RAM forces plastic into the heating chamber around the spreader. This is a spreader, and where the plastic melts as it moves forward because of heat. So molten plastic is forced and pressure injected, we call injected into the mold cavity where it assumes the shape of the mold. The shape of this mold. This is a nozzle. This is a feed hopper. This is a pellets. These are small pieces of this is a polymer. This is a hydraulic pressure, barrel, and heating chamber. And then we call it another way. One is extrusion. Right? So this is extrusion. And for thermoplastics, plastic pellets, still small, very small pieces, drop from hopper onto the turning screw. This screw is turning. That means when the screw turns, so these pellets are fed from here to here. And so plastic pellets melt as the turning screw pushes them forward by the heaters. These are the heaters. Molten polymer is forced and pressure through the shaping die to form the final product. We call this extrudate. So turning screw, barrel, molten plastic, extrudate. So these can have tubing and pipes, sheets and films, and structural parts. Another one is a blown film extrusion. So this here is, for example, here heaters extrudate. This is a tubing die, right? So this air, we put air here. So this air bubble, and we have air here also. Look at here. So this is air bubble, the guide rolls, pinch roll, air bubble, and then we have this is a film, and bags, film, and sheets. And so this is a very important one. And polymer types, fibers. Fiber, okay, for fiber we have we call fibers when the ratio of length to the diameter is greater than 100. And so primary use is in tactiles. The fiber characteristics, high tensile strength, high degrees of crystallinity, and structures containing polar groups. So formed by spinning. Extrude polymer through a spinner rat, a die containing many small orifices. The spun fibers are drawn and tension leads to highly aligned chains, a fibrillar structure. So like fiber-like structure. And another one is miscellaneous coatings. Okay, coatings. The thin polymer films applied to the surface, for example, paints, varnishes, protects from corrosion or degradation. And another one is a decorative, improves appearance, and can provide electrical insulation. So these coatings are very important. So adhesives. adhesives. This bonds two solid materials. Adherents. So bonding types: secondary, van der Waals force. So these van der Waals force are usually very weak. Mechanical penetration into pores or crevices. The film produced by blown film extrusion are foams, gas bubbles incorporated into plastics. And advanced polymers, an ultra-high molecular weight polyethylene. So molecular weight is MW based on the weight, is 4 times 10 power E gram per mole. And outstanding properties of this material include high impact strength, resistance to wear and abrasion, low coefficient of friction, and self-lubricating surface. That is very, very awesome. And so this is very, very useful for the implants and people are using. Important applications: bulletproof vests. These vests can be provided to the police officers or our soldiers, and golf ball covers and hip implants. So this is very, very important. Advanced polymers. Another one is a styrene butadiene block copolymer. So this is name is very, very long. And thermoplastic elastomer. So this is styrene. This is butadiene. And so this is hard component domain here. So this is soft component domain here. You can see the summary of the polymer limitations of polymers. So Young's modulus, yield strength, and this is critical stress intensity factor along with operating temperature are generally small or low. And deformation is often time and temperature dependent. And for thermoplastics, they have smaller Young's modulus, yield strength, and operating temperature, and larger Kc because it is ductile, and so the critical stress intensity factor is usually high, and easier to form and recycle. And for elastomers rubber, large reversible strings. So this is very, very cool. For thermostats, for example, epoxies, polyesters, and they have larger Young's modulus, yield strength, and operating temperature, and smaller Kc. Because as I said, the ductility and the strength, and these are two competing mechanical properties. If one is high for the same material, the other must be low. And you cannot have a material that possesses higher one and higher strength and higher ductility. If you tell me this, and I will ask you to show me where do you get this material, this information. I'm kidding. So the convention is, so these two mechanical properties, I mean ductility and strength, they are competing. And if you have a material, you can have either high strength and low ductility, or low strength, higher ductility, or you can have decent strength, decent ductility. You cannot have high ductility and high strength as simultaneously. So here is a table, okay, and a good overview of applications and trade names of the commonly used polymers. And you can just take a look at this table 15.3. Thank you very much for your attention. And summary, this polymer processing, compression and injection molding, extrusion, blow on film extrusion, polymer melting and glass transition temperature, polymer applications, elastomer, coating, films, fibers, adhesives, foams, along with advanced polymeric materials.